as I went around and looked at homework, I'm looking for certain problems where I know there might be issues. I'm looking for certain things. One that jumped out at me was 19. 19 is one I'm fully prepared to talk about. Number 19, there it is drawn here. I knew that was going to be one. But I didn't have very many people come in and ask. Now, if that was the only question you had one or two questions, maybe you don't think it's a big deal, maybe it isn't. But I had like one person come in and before school. I had nobody come in at lunch and ask any questions. And that's okay because we will go over some things in class, but often it's not enough for many of you. I mean, so take advantage of those opportunities. Number 19 is an odd problem. Obviously, most of what I saw, it looked like you just wrote it down from what you saw in the back of the book, which, that's fine, but just understand that, if you don't understand what's going on with a problem, that, at this level, it's really about understanding what is going on. And even if you kind of got it, but not really, even come in and ask about that. And maybe it'll more fully kind of fill in the gaps of what was going on. So you really have to be honest with yourself about what you have questions about and what you really do understand. So a couple of them that we definitely want to look at. I think one is number 12. We probably start there. That's the one that I told you will definitely have on the quiz, is a piecewise function. So let's start with that one. Now, a comment here. I think this is just strictly a kind of a typo, a misprint. This was supposed to be right here at -3. Now, if you're like the other class, some of you just assumed it was at -3 and just went with it, and some of you were more particular and that kind of thing. And this is supposed to go right up here and hit this point. So whenever I give you a piecewise function on the quiz, they're gonna land at nice, neat points, nice, easy slopes to do stuff like that, okay? So we're doing a piecewise function here. So whatever, I'm not sure what they call this function, we'll just call it f. It's three pieces. It's a line, a circle, and another line. This line would be the line y equals -2, but we already have the y equals here, so all we put is the -2. And that goes from -5 to -3 is what I would call that. If you put -2.9 or whatever, don't worry about it, that's fine. But just, I'll remind you that on the quiz. Then we got the circle. I'll leave that one here for a second. Then we got this line. Looks like it's a slope of -2. Looks like it goes through the point 2, 2. So that'd be x minus 2 plus 2. And that seems to go from 2 out here to 5. And we do have to include that 2 for sure here. We had the discussion yesterday about, where the circle and this line take off. You could include them both. I probably won't make a big deal about that. But here, you definitely have to include the 2. And on the circle, you do not include the 2. That's very important. Okay, here we got our circle now. We got x minus 0. I think the center would be down here at 0, -2. So x minus 0 squared, y minus -2 squared, which would be this, and the radius is what? 3. So there would be our circle equation, but we got to solve that for y. So we need to move, that's just going to be plain old x squared there, so let's subtract that over to the other side. Now what? Square root both sides, and remember it's plus or minus. But in this case, what's the plus, well in any case, what's a plus or minus mean on the circle? Top, bottom half, right? We want the top half, right? Even though we don't have the whole top half, that doesn't matter, we'll take care of that in the other part. So we want the top half, and then I got to take away 2 from both sides. So we have -2 plus the square root of 9 minus x squared. Remember, we talked about how you can't square root the pieces there, so you can't have 3 minus x, for example, right? It's just square root of 9 minus x squared. So there's my y equals, so I'll put that over here. So I'll have -2 plus square root 9 minus x squared. And then, and if this, this is x minus 0, but if that would have been like x minus 7, quantity squared, I just would have left that quantity squared. And then here I'd have a 9 minus the quantity x minus 7. I mean, you could FOIL it out if you want to, but it's kind of silly. It just would make it a lot more difficult. But and then this would start at -3 and and go to 2, but we would not include the 2. You want to include the -3, include it. You don't want to. It's got to be included on one of those first 2 equations. Yeah. Because on the circle? Yes, because it's the top half of the circle. If we were down here, then we would have used the minus. Okay? Yep. The plus or minus is top bottom. If it's not the complete half, we take care of it with this right here. We said we go from -3 to 2. Yeah. Because that's what we're saying. We're saying, hey, we have the top half of the circle, but we only have the top half of the circle from here. Yeah, exactly. And you would never have partly top half and partly bottom half, right? Because what would happen? It's not a function. It's not a function, right? It fails the vertical line test. So you're never going to have part of the top half and part of the bottom half. That can never happen. This -2? This one. Oh, this line right here. That's just the line. That horizontal lines look like that. Vertical lines are x equals. So it was just that piece right there. Yeah, that was just the y equals -2. Yes, good question. And that, a question like that is very important to ask. I mean, I'll go through and I'm trying to pick out some of the harder stuff, the stuff that I thought would. But sometimes there's little things that just nag at you, and you're like, God, I bet I'm the only one that's got that question. You've got to ask those things. If not in front of a big group, then individually, too. When we have some work time, stuff like that. Get those out of the way. I had somebody who came to me one time, they wanted to drop at Christmas time. And her reasoning was, when we first learned it, I can't remember what it was. There was something we learned early on, and I just never got that. And I was like, and I said, are you kidding? That was like 8 weeks ago, 7 weeks ago, and you just now telling me this, right? This has been bugging her for 7 weeks, and she never had asked me about it one time. Spencer, what's your question?
What's the -2 in front of the square root?
-2 in front of the square root came from right here. We took away 2 from both sides. Why is it behind the square root? It doesn't matter. Let me tell you why I do that. If I could have went square root 9 minus x squared plus 2, but sometimes we extend that square root like that, and then it's like, is that 2 under or is it not under? Where is it? So just kind of out of habit, I move it there, but it doesn't matter. Doesn't matter.
So like this might be like an off-topic question, but like x on our calculators, I was just trying to split it from yesterday.
Yeah.
And I noticed that you can't really. How do you make a vertical line?
Great question. Because on your graphing calculators, you are graphing functions. And a vertical line is not a function, right? I mean, vertical line really fails the vertical line test, right? In a big way. I mean, it's just, so I think there is, you did?
Yeah, you go to menu.
Oh.
And the graph entry, no, it's equation.
Under, yes.
And then line, and then there are different types of lines and parabolas and circles and such. And then it would be
That's awesome. Thank you, Alex.
Yep.
This is this is a great time to look at this. Does anybody, when they go to menu, go to the graph screen, go to menu, does anybody's not say graph entry /edit? Does everybody say that? Okay, because there was a software update early last year that changed these menus. Just says graph. Okay, so I need to update your software. Okay, because they did change this and they added some things in there. So when it says graph entry, and then right here, see, because we can graph functions, but we can graph a lot of other things too, and we'll use some of those this year. But under equation, it can do parabolas, circles, ellipses. It's pretty cool. It'll just give you the form you do them. Now, for our class, we don't use a lot of those very often. But there it is, line, yeah. And we can do x equals c, and then what happens is it turns into this. Yeah, very good. I'll be honest, we don't have occasion to do that very often because hopefully vertical lines horizontal is pretty easy to draw that in, so not very often do we actually draw them on our calculator. But there it is. Cool. All right. So now let's move on here. Another one that I wanted to do was number 22. We are going to do 19, but I want to hold off on that in a minute. Number 22, I think most people's question was probably part C. But the absolute value graph is just the old V graph. Now, one of the things we'll spend a lot of time tomorrow working on is what I call the elementary functions. We really need to have an understanding. Now, for this first quiz, not so much, but we really need to have an understanding of basic elementary functions. We need to know what the absolute value graph looks like, the x squared graph, the sine graph, the cosine graph, the square root graph, the e to the x graph, the natural log graph. I mean, they're just some of the basic families of functions. We need to know what their basic graphs look like. Okay? And so we're going to talk about some of those tomorrow. And we're going to, hopefully as we use them, we're going to get better at them. Now, I have decided on the quiz, I think I've been saying that this first quiz would be all no calculator, but as I thought more about it, a lot of the stuff we'll be doing, we don't need the calculator. I just give you a graph, or give you a piecewise function, or give you these things. And so you don't really need the calculator for any of that. But so it doesn't hurt if you've got it, because it doesn't really help you any. But there are some things I think I want you to be able to do a graph. I want you to be able to put an equation into your calculator, draw the graph, and then maybe answer some questions about that. So I think we will do the calculator. So by Tuesday, you have to be comfortable going onto your graph screen, putting in an equation, setting the window, okay, and looking at a graph, maybe being able to trace on it, okay? So we want to be able to do that by the quiz on Tuesday, all right? So anyway, back to the V graph. So here's our absolute value graph. So the domain is what? All reals. Now you can write out all reals if you want. This is a good way to say all reals also, negative infinity to infinity, okay? But you can write out all reals if you want to. The range, greater than or equal to 0. So all real numbers greater than or equal to 0. You can write that out. You can use a greater than or equal to sign. That's fine. Now, if you do, don't put an X. You should either put f of x or y or something like that, or write out all real numbers greater than or equal to 0 somehow. But in notation, it would simply be this. 0, using this notation, right? That's what we'd be talking about. Because it could be 0, and it could be greater than 0. All right, and then finally, piecewise function. Well, think about it. Absolute value graph is really just two pieces. It's two lines, right? What's this first line? It's y equals what? It's just negative x, right? It's a negative slope. It's got a y-intercept of 0. It's just negative x. I mean, I could pick a point and put in there and put it in point slope form, and that'd be fine. It would simplify to the same thing. Somebody was telling me they used the point negative 1, 1. So they did this. They went negative, and then they did x plus 1, and then, yeah, that'd be right. They did that. That'd be fine. But it's really just y equals negative x. So here you'd have y equals negative x, and that's from negative infinity to 0. And then what's this line? Y equals x, right? Slope of 1. And then that goes from 0. I usually include the 0 on that one. Doesn't really matter. 0 to infinity. Right? Probably never even thought of it that way. But that's what absolute value is. If you think about it, what is it? It's, well, when you put in a negative to absolute value, what do you get out? Positive, the opposite. So, put in a negative, you get out the opposite of x. If you put in a positive, you get the same thing out, right? You put in x, you get out x. So that's what absolute value means. It's a piecewise function. It's just two lines that make a V. Okay? So that's what they wanted in part C. Yeah, baby? On infinity? Yes. Because you can never, infinity is not a number. You cannot get to infinity, so it can't be a closed. Yes, you would miss that. That's been on the AP test before, too. If you put a closed bracket on an infinity in an interval, that will be bad. Yes. All right. Yeah, bad things will happen. All right. One more here, and then we'll do number 19. Number 28. Number 28. So probably would be good. Let's see how close I came to seeing having those lines right on there. No, not very close enough. All right, let's try. Now that's pretty good. Does somebody else want to try? I mean,
How do I get it?
Oh my gosh. Okay, now you draw one going across it.
Down a little farther, down a little farther. About the, there you go. Okay, stay right on the line.
Oh.
And you're recording class today, aren't you?
Oh yes, yes. Once again, this will be on YouTube. For,
Are you ever going to record seconds?
Sign it, Miranda. Sign your name.
oh, probably. Okay. All right. That's
Yeah.
pretty good. All right. Okay. So we're supposed to do this piecewise function. So it's y equals 0 if x is less than or equal to -1. So that would be this line this way. Okay, that'd be just right on the. That'd be a horizontal line right on the axis, right? Y equals 0. And then we get the line 3x minus 2. Now, if I'm graphing one of these, what I want to do with this typically is just, I want to graph the whole line, but we really only want it from 1 to 1.5. So it's got a y-intercept of -2, so I just put some small points here. It goes up 3 over 1, up 3 over 1, up 3 over 1. But I only want the piece that goes from 1 to 1.5. Now, it doesn't include either one of those. So I'll be an open circle there. And let's see, 1.5, I better plug that in. It's really just plotting points is all you're doing. So you put a 1.5 in there, that'd be 4.5 minus 2, that'd be 2.5. So 1.5, 2.5. So that would be this point right about there. So all we really want is that piece of that line right there. Okay? So just plot points. All right, the next one's x squared, which is a parabola. So that's a parabola, you know, is gonna kind of curve a little bit. But we're only going to look at a piece of it, so it'll almost look like a line. It'll be hard to draw. I mean, if I give you this one on the quiz, I'll give you a little leeway for your drawing. My drawing's not great either. But the parabola, we only want to go from 1.5 to 2. So 2 squared is 4, so that'd be this point. And we don't include that, so that would be an open circle. And 1.5, what's 1.5 squared? 2.25. So 1.5, 2.25 would be right underneath this. And then it would kind of curve a little bit. It's a parabola. So it kind of curve around that and go about there. So we'd have this horizontal line. We'd have this piece of a line here. We have this little piece of the parabola there. And it is a function. I mean, it passes the vertical line test. I mean, if this was filled in, then that would be no good. You'd have 2 outputs for that one input. But right here, that's open, that's closed, so that's fine. It's got a gap here where there's no function. What would we say about the function right through here? Undefined, right? There's no output there, so the function's undefined between -1 and 1. Function's undefined past 2, right? It has no outputs there, so the function's undefined in those places. So there you go. Just sketch something like that. All right, let's do number 19 then. And then when we have some more time, if there's some other ones that you didn't get answered, you can come back to those. All right, here's 19. Now, this is the book does a really good job of foreshadowing some things that we're going to do down the road. We did that with our appendix problems, with Appendix G. Remember those story problems? We said we'll be doing stuff like that. Well, this is chapter 5. Remember we did area, that exploration 3 and 4? We talked about area under the curve. Well, that's what we got here. This is what they described. Now, a lot of you never drew this picture. A lot of you didn't maybe see what was happening, but some of you did. I did see some good stuff as I walked around. They tell you have the line 2x plus 1, and the a function is going to be the area under that, the trapezoid area that's under that. So that's that red trapezoid is what we're talking about. But t is the right edge. It said it was bounded by x equals 0 on the left, or y-axis, and bounded on the right by the line x equals t, and bounded above by the blue curve, 2x plus 1. So there's the trapezoid. So you really, I think it's really helpful to have a picture. Well, the area of that trapezoid is our new function. Now think about it. What's a function? Well, it's a rule that defines an input to an output. Well, our input is the right edge. That's kind of weird. We haven't really thought of things like that before, but the input is our right edge, so that right edge can move. Every time the right edge moves, we're at a new input. And every time the right edge moves, we have a new what? New output, new area, a new trapezoid. And every right edge will have how many areas? Just one area, right? And that's what a function needs. One input, only one output. So every time we move the right edge, we'll get a new area, and that'll be the output. Well, the area of a trapezoid, we did that the other day.
That's just 1/2 B1 plus B2 times H. So all we have to do is work that out. So, I should do that correct. So our area function is 1/2. Now what's B1? Well, B1 is this height right here, this Y value. What is that? How do you get a 1? Well, yeah, I mean, you could just look on the graph, but even better than just look on the graph. Plug a 0 in right here, right? You'll see what I'm saying is, plug a 0 in for x, and you get the y, which is 1. So that's the left-hand base is 1. What's this base? What's this y value? 2t plus 1, right? We don't know what it is because t can move, t can change. So we don't know what that height is, but we do know that it's whatever you get when you put a t in for x. In other words, if this was 3, this height would be 7. You know that because you put a 3 in for x. If this was 4, put a 4 in for x, this height would be 9. So if the right edge is t, we put a t in for x, we get 2t plus 1. So the right edge is going to be 2t plus 1. Okay, and then what's h? That's this. Well, that's t. From 0 to t is t, right? If this was 3, if this was at 3, the h would be 3. If this was at 4, the h would be 4. So it's just t. Okay, there you go. Well, now we just have a little simplifying to do. Inside the parentheses, you would have this. Distribute the 1/2 through there, you would have 1 plus t times t, and then distribute the t through there, you'd have t plus t squared. And then now you see that's why in number 19 in the back of the book, they had t plus t squared. That's what it came from. Okay, came from the area of a trapezoid. All right, and then you're supposed to graph it, and I'm not so concerned about that. You just go into your calculator. Remember, you can't use t when you graph something in your calculator, you use x, right? And then it's a parabola, you know, so that's fine. Which makes sense. Why would the area, this is something we'll talk a lot about later, why would the area of this trapezoid curve up like that when you graph that equation? Why would the area graph curve up? As you move this way, as t moves this way, what happens to the area? It gets bigger, but now it gets bigger, but gets bigger faster, right? Because think about it this way, every time you move over 1, you gain a bigger chunk of area, right? And then I move over 1, I gain a bigger chunk every time because this line's going up like that. So every time I move over that right edge, I gain bigger and bigger chunks of area. It's going to make that area graph go up steeper and steeper, right? All right. Okay, let's move on. Go ahead and get your notes out, I suppose. Yeah, Aaron? No. But we've had a few of those, haven't we, that have been parabolas. And the only reason for that so far, well, I can't really even say that with our example. No, they're not. They're not. Yes?
Why would the area increase exponentially if it's just a straight line?
Why wouldn't it? Or
Why would it?
why it doesn't increase exponentially, actually. There's a difference between, now, this is exponentially, and this is a parabola. See the difference? Seriously? I was kind of joking. I didn't really see much of it. You're right. It exponentially be like e to the x. E to the x. And that's a really good question, actually. If I have this and this, as x gets bigger, these both get bigger, right? But which one gets bigger faster? You ever think about that? I mean, for small numbers, they're pretty close. Like 3, 2 to the second is 4, 2 to the second is 4, right? Put in a 3, that'd be 2 to the third is 8, and this would be 3 squared, which is 9. So this one's getting bigger. Put in a 4, 2 to the fourth is 16, 4 squared is 16. Put in a 5, 2 to the fifth is 32, 5 squared is 25. Pretty soon, it doesn't take very long for this one's getting way, way bigger, right? You ever heard that thing, if you had a penny every day doubled for a month? Yeah. And it doesn't seem like that big a deal, but all of a sudden by the 28th, 29th day, it goes crazy, right? So as x gets bigger, this gets bigger way faster than this does. So when you said exponentially, these both look like they're getting bigger exponentially, but this one really gets exponential. When we say exponentially, man, it gets really big. Probably just kind of wander along kind of thing. So since it was a line, you're right, it would not get bigger exponentially. It would get bigger in just kind of a non-exponential. I can't think of a good word for it. All right, we're gonna jot down some notes here from section 3, okay, or section 2, excuse me, section 1.2. So you might want to follow along in your book. There's a lot of terms and stuff in here that I don't think are that important for you to write down. They're all in boldface, and most of them make perfect, just kind of common sense. But I'm looking at page 12 here, okay? Looking at page 12, and we'll write down some stuff. Some of this is review. Some of this was on that algebra sheet that we did at the very first day when the sub was here, about shifting and moving graphs and stuff like that. So hopefully some of that's review, but we'll go through some examples and you'll get a chance to practice them in the homework. So the first picture, or the first thing I'd like you to look at here is on page 12, you've got this picture here. And just notation, okay? When you have points on a graph, you've got A, F of A, B, F of B, right? We're getting away from saying X and Y. We're talking inputs and outputs. So when you see F of A, F of X, F of C, you think output. Okay, so A, B, C, those are the inputs. F of A, F of B, F of C, those are the outputs, the Y value. Okay, so just some of that notation. Down at the bottom of page 12, it talks about continuous functions. We'll talk more later about the details of what continuous means. Continuous for you just means no breaks, no gaps. Kind of like those piecewise ones we looked at that have the gaps in them and the stuff like that. Those are not continuous. Most graphs like this one that we deal with are continuous. Nice and smooth, like the sine graph, the cosine graph, parabolas, stuff like that. Okay? All right, the next page here. Skip over that. Okay, we'll look at the middle of page 13. Before we get to this one, before we get to this picture, if you look at the middle of page 13, it talks about x-intercept, y-intercept. Hopefully those are easy terms for you. Talks about increasing, decreasing a little bit. That's important. Down at the bottom of page 13, maybe I'll draw this. This is a pretty important graph. Let's look at this. If I had a, oh my goodness. Okay, I can't, that'll make me dizzy. Jeez. All right, that's not bad. So if I have a, I think it's not my fault. I think because I'm recording this, the computer's lagging or something like this. All right, good enough. All right, so right here, call that point C, and call this point B down here. All right, there are some terms on a graph that we want to, that are kind of important. Like right here, where it crosses the x-axis, this is called a root of an equation. So C wouldn't be a root, it's a little below there. Right here is a root, and right here, just above C, that would be a root. So anytime that where a function crosses the x-axis is called a root, so x-intercept and root kind of goes together. Sometimes those are called the zeros of the function, right? Because that's where the output is 0. It's where the y value is 0. So when we say the function is 0, we mean its output, right? This point A up here is called a local max. Point A is called a local max because it might not be the highest point on the graph. Matter of fact, if this graph goes up and down forever, it's definitely not the highest point on the graph. But in that local, in that small region, A is the highest point. Okay? And the same thing down here with B, even though my picture doesn't look like it's quite the lowest point. Local minimum. That's called a local minimum. So that's a term we'll talk a lot about. We'll be interested in those points. I mean, think about the thing we did with the coffee mugs yesterday in Appendix G. We were looking for the max profit, so we wanted that highest point on that graph. So local max, local min. Those are important terms. Okay? So I kind of am over on page 14 now. C here is called the inflection point. Remember we were talking about the balloon the other day? if this was the altitude graph, like with the balloon, what was happening at sea with the balloon? It was going the fastest, right? Its velocity was kind of the max. That's when it was going the fastest because the graph was the steepest, right? So we're often interested in that scenario as well. That's called the inflection point. And that's where the curvature of this graph changes. See, this graph is curving down until there. That's called concave down. So when a graph is curving like this, that's called concave down. Like a spoon upside down. Okay, a spoon upside down would be concave down. And then, of course, this section then is concave up. Concave up. All right? So concave down, concave up, and an inflection point is where that switches. Okay? Where that switches. And that'd be where the balloon was going faster and faster and faster until it hit its inflection point, and then it started slowing down. Okay? Still going down, but it was going faster, faster, faster as it went down, and then it starts kind of slowing down until it gets to point B, where it eventually starts going back up. Okay? So those are just some terms of graphs, all right? Won't be a huge deal on the quiz, but could be something terms you want to be familiar with. Okay, here is a graph on page 14. Another thing I'll probably do on the quiz is just give you a graph with some story problem kind of attached to it, tell you what it's about. This is an epidemic, say a flu epidemic, in a population, in a city maybe, and you have people that are susceptible, people that are infected, and people that have recovered. Okay? And I just might ask you some questions about it. Simple questions to be on day 15, how many people are infected, and be able to read off of that. Or maybe make some other kind of observation about the situation. In the beginning, most people don't have it, so most people are susceptible. A few people, 3,000 or 4,000 maybe, are recovered already, right? Because time zero was, we said, okay, we got some people that are sick. Well, and they've been sick, and okay, this is time zero. We go back, we'll call this day time zero. Some people already had it recovered, some people are infected at that time, a few. Okay? Right up here, is when the most people are infected. Somebody asked this question in the other class. I thought it was a good question. They said, how come the number of people recovered is higher than the max that were infected? That was their observation. So what would you say to that? Aaron? Yeah, this isn't the total. This doesn't mean 30,000 total were infected, right? It just means at that time 30,000 were infected, right? So then they followed up. They said, well, there's 50,000 plus a few here that were infected. Say there was 3 that were infected, 3 that recovered. So there's a total of 56,000 people here, right? So my comment was all 3 graphs probably should never add up to over 56,000. Does that make sense? Like right here, there's 30,000 infected. There's about 18,000 recovered. What's that, 48,000? And there's about 8,000 or 9,000 susceptible. What's that at? About 56,000, right? About 56,000. That would kind of add up to the total population. Over here, you've got about 38,000 recovered. You've got about 18,000 infected. What's that? About 56, wasn't it? And then hardly any, and nobody left here. Almost everybody's got it, right? So that, again, that adds up to pretty much the whole population. So, so things like that. When were people catching it the fastest? When were people getting infected at the fastest rate? Where would that be? Back in here somewhere? Right? Or what about, well, that's where they're infected. What about when the susceptible numbers were going down the fastest? That's kind of in here. Now those don't seem to match up too much on that graph. You'd almost think those would line up a little bit. Okay, but anyway, just an example. Here's a graph in context read some things off the graph and be able to say some things about the situation or answer some questions about the situation. Okay, moving on. Page 15. There's that table of data that we talked about yesterday. With no context, that's all we know about that function. And so they give you some graphs. They said it could be any of these things, right? That table of data could be connected. It could be a piecewise. It could be a smooth curve. Who knows what's going on in between those points? So without some additional context, we don't really know what's happening. Okay, probably one of the more important things that we'll have in this section is coming up next. So the next page, as we turn to page 16, I'm going to send you a couple of documents here, and we're going to go through them together. Now, it's not a big deal to do much with these, but if you like, if you're a hands-on person, if you like to look at these things, this might be helpful. If not, you can maybe just follow along with me up here and not worry about it. But I'm going to send them to you. So this first one is called translating functions. When you get it, just choose close probably. Well, this one you could open. Translating you could open. You can only have one open at a time. And I'm going to send you this one called dilating. And when you get this one, I would say just say close on that one. So we want to be looking here first at the one that says translate. Is everybody getting it? I did not get it. Slowly it's thinking. Spinning wheel. Okay, what we're talking about here is we're talking about this shifting and stretching of graphs, all right, and how that works. And I'll show you some things that we'll write down here. How are we doing? Are we getting it? Anybody still spinning? A few people. Okay. Well, once you get there, you can hit Control and right arrow, which will take you to the next page. Okay, and we have a simple parabola here. Now, the first thing I want to do with this parabola is I want to grab this point down here. Now, as you arrow, and this is where you have to use your trackpad a little bit, and it's a little easier for me here with this than it is for you guys. And you get your hand over top of that, and then if you hit enter or press the middle of the trackpad, I believe it'll close, and then you can drag it up. So like drag it up 2. And you drag it then, once the hand closes, you can just drag it by, moving your finger on the trackpad. Okay, once that hand's closed. Okay? And look what it does to the equation. It makes the equation x squared plus 2. So it adds a 2 on the outside of the function. If you drag that down, right, it's minus. All right? So that's just a simple example. So in your notes, if you want to write something down here, this would be a vertical, what I'm going to call a vertical shift. Now, the fancier name is translation, but that's a vertical shift. And that's when you take and add, okay, that's when you add or subtract something from the outside. So if you add, it moves it up. If you subtract, it moves it down. Now, the way I like to remember vertical is if it's on the outside of the function, it affects the output. It's on the outside of the function, it affects the output. So it's going to affect the y, the up and down. Okay? All right, now let's grab that thing and let's move it horizontally. Let's move it 2 to the right, over on the x-axis like so. Okay? And look what it does. You got an x minus 2 inside of the parentheses. Well, that makes sense. It worked on the input. The minus 2 is on the inside, which should affect the input. The input is the x. It should move horizontal. But it's opposite of what you think, right? A minus you'd think would be left, but it's not. It's right. And a plus would be left. Now, you guys have dealt with that before with parabolas and things like that. Circles and, whatever. So in our notes, though, let's write this. So a horizontal shift is on the inside, but it's opposite. A minus would be a right, and a positive would be a left. So those are the two easy ones, the shifts or the translations. All right, now, later, on your own time, if you want to, you can mess around with this. If you go to the next page, what they do on the next page is they give you, on 1.3, they give you some vertical shifts. So they give you a V graph. You can grab this K slider here and you can slide it up. And you can see what it does to the equation. Then you can click the little triangle there and it'll give you a piecewise graph. You can slide it around. And see how that would change a piecewise graph. How it would just shift it. And then they give you a polynomial graph and another kind of graph, whatever. Okay? And then if you go to page 1.4, they just give you some horizontal shifts. That's a square root graph right there. Top half of that parabola. And shift it back and forth. Or you can look at it, that'd be a cubic graph. That's a log graph right there. That's a log graph that's been shifted over. That right there is a natural log graph right there. That's one of those graphs we're going to want to memorize. That's a natural log graph. There's a parabola, and so forth. And then I think there's one more page where you can play around doing both. You can take a graph and do a horizontal shift. You can do a vertical. You can kind of see how that affects the equation. Okay? So it's just kind of something you can get your hands on a little bit and play around with. All right, let's go to the other one. So you probably go back to the home screen, go to My Documents, and open up the one that says dilating. Now, it'll probably ask you if you want to save the other one. I would say no. I don't think there's a reason to save it, but you can't. That just means all those movements and stuff you did would get saved. Okay, so if we move to the next page on dilating. Okay, so dilating is a fancy word in my mind for compress or stretch. So if we put a number on the outside of a function, it should affect it vertically. And sure enough, watch what happens if I grab this and move it up. See, they call that a vertical stretch, and that's what I would call it. So if you multiply on the outside of a function, okay, so I'm going to call this a vertical stretch. So if I have a times f of x, that's a vertical stretch. Now it's only a stretch though if a is greater than 1. If a is greater than 1, that's a vertical stretch. It's a compression if a is between 0 and 1. Like a half or a third or a fourth. And you can see that we'll see that in the calculator document here in a minute. So we have a vertical stretch. If you multiply on the outside, but again, since you're doing it to the outside, that affects the output, so it affects the y. And it affects it the way we think. Bigger numbers are going to stretch it. Littler numbers are going to compress it. I'll come back to this in a second. So there's a vertical stretch. If I grab this thing and I move it down, so there's a half, there's a third, they call it a shrink, or compression. It makes it fatter, right? If we do that to a parabola. Now, what happens if it goes negative? Now you've got a flip, or a reflection. So if a is negative, so let's go back to the other thing here. So if a is negative, less than 0. If a is less than 0, it's a vertical flip. So if a is negative, so you could have both a flip and a stretch or a compression. So if you had -2, that would be a stretch of 2 and a flip, which you can see over here. So if you have a -2, that's a stretch and a flip. And if you have a -1/2, that's a compress with a flip. Okay? So you can see how if we know what the basic graphs look like, and then we put these other numbers in there, we can get a pretty good idea of a whole bunch of different graphs. Okay, if we go to this one, now if we go to the next one over, this just gives you some different ones to look at. It gives you a parabola you can look at and you can stretch. I think then it gives you a V graph that you can stretch and compress and flip, right? That kind of thing. It gives you this is the square root graph, top half of a parabola, stretch, compress, flip. Okay? Now what it doesn't do, what this document doesn't do for us is do horizontal. So we'll just look at these ourselves. So a horizontal stretch or compress. Now, looks like this. If you have an A on the inside, that's, if it's on the inside, it affects the inputs, it affects horizontal, the x's. But it's the opposite, just like horizontal shift. So if you have A greater than 1, you have a compression. It works the opposite. So if you have a 2 in there, it's actually going to compress the graph by a factor of 2. If you have a 1/2 in there, it's actually going to stretch it. So if you have a 1/2 on the inside, it actually stretches it horizontally by a 2 factor. Okay? It's like the reciprocal. And what do you suppose if it's negative? Horizontal flip. Yes, a y-axis flip. It flips around the y-axis. Okay? So there you go. Now I want to talk a little more about that horizontal, because that's always a little tricky. So, and some of them, a horizontal and a vertical stretch or compress are kind of related. For example, if you had 2x quantity squared, so that should take a normal, sorry to Dakota. Sorry, Dakota. We'll put this on. All right. Like he's going to watch it anyway. All right. So if I had normal parabola, 2x quantity squared, right? So normal parabola, this should compress it by a factor of 2, which would mean it would, look something like this. Well, what else does that look like? A horizontal compress looks like a vertical stretch, right? Well, of course it is, because what could this simplify to? 4x squared, which is a 4 on the outside of x squared, right? Which should be a vertical stretch. So a vertical stretch by a 4 factor is the same as a horizontal stretch of a 2 factor, and that makes sense because 2 squared is 4, and so that's where that comes from. So sometimes something is both a horizontal compress and a vertical stretch at the same time. Okay, same thing would be true on absolute value graph. Now where that's not true is like a trig graph. If you have sine 3x, that's much different than 3 sine x. You can't just, you just can't pull that 3 out of it. Okay, let's do the easier one first. 3 sine x would be what? Here's a normal sine curve, goes up to 1, down to -1, right? What would it do? What would a 3 on the outside do? It would go up to 3. But it would still cross at these same places. It would still have the same roots, right? Because what you're doing is making all the positives 3 times as positive and all the negatives 3 times as negative. So it's stretching from 0. So at 0, it's still the same. Okay? Well, what would this look like? Here's, again, your normal sine curve. These are a little harder to do sometimes. So this point right here, which is at pi, which is rough, let's call it 3, this is going to compress by a 3 factor. So this point, instead of being at 3, will be where? At 1. This point that's at 6, roughly, right, 2 pi, what do you get if you compress 6 by a factor of 2? 3. So this point will be roughly right there. So this sine graph is going to go up to 1, down to here. Wait a minute. No, we're by a 3 factor. We're compressing 6 by a 3 factor, which will take us to where? 2. So it'll be right here. So it'll come down and it'll go up. So that's what your new sine curve is, right? So here a horizontal compress is not the same as a vertical compress, right? When you take the sine graph and compress it, it doesn't make that sine graph like a balloon would, right? You squeeze a balloon and pop up. That's not what's happening. It's compressing it this way, so those y values stay where they are, just like that, okay? Same thing was happening here when we compressed that, okay? But it ended up being the same as a different type of stretch, okay? So here's your vertical stretch on this one. Here's a horizontal compression on that sine graph. So everything squeezes in, but the y values don't go up or down any higher than they would have been. Okay, so you're going to be given a graph, just some lines or some curves or whatever, and it's going to have you do these different things to it. Stretch it, compress it, shift it, right, flip it. All right, so that's it with that. So we've got a couple other terms to go over, and then we'll have some work done. Okay? So, because we're talking about graphs, talking about functions. Okay, here we got 3 other terms to review. And these are review, actually, because I think you learned about these last year. This is an even function. An even function. Now, I'll give you a couple of examples to help you. Okay? Y equals x squared is an even function. Cosine is an even function. Okay, somebody want to tell me what makes something an even function? What property do those two pictures have? Yes, Richard. Y-axis symmetry. They are mirrored on the y-axis. That is correct. So, if I put, sometimes I like to draw it this way. If I go over and up that much, I would go over and up that same amount. Same thing over here on cosine. But that's just showing y-axis symmetry. Okay, another way of saying that is opposites in, same out. Right? You put 2 in and square it, you get 4. Put negative 2 in and square it, you get 4. Opposites in, 2 and negative 2, same out. You get 4 out. Okay? So if something's an even function, then we know some things about it. Okay? So if I tell you that f of 2 is 8, so if I ask you on the quiz, I give you a function, I say f of 2 is 8, what's f of negative 2, what would you say?
8.
It's 8, right? Very simple. Should be an easy question, right? The fancier way of writing this is f of negative x is equal to f of x. That's another way of saying opposites in, opposites out. The outputs are equal. Excuse me, opposites in, same out. So you put in 2 opposites, x and negative x, as inputs. And their outputs, f, are equal. So that means opposites in, same out. Now, where that's useful is, well, let's look at a couple of examples. Negative x and square it, isn't that the same as x and squaring? Right? They both come out to be x squared because a negative times negative is positive. And that's also true of cosine. Now, that's one we forget about sometimes. But cosine negative x and cosine x are the same thing because cosine's an even function. Cosine of pi halves, cosine of negative pi halves are the same thing. Okay? Cosine of pi fourths, cosine of negative pi fourths are the same thing. They're even functions. All right. So let's do an odd function.
So we can do a couple of examples. Well, wait a minute. Instead of that, the even function has y-axis symmetry. Then, of course, an odd function would have. Oh boy, you guys are suckers, just like second block. I thought for sure
Except
since you were
it's not
mad.
a function.
You can't have x-axis symmetry, right? Because what would happen? It wouldn't be a function, right? It wouldn't pass a vertical line test. You'd have something like that, right? And you can't do that. So that was mean of me. I shouldn't have led you into that. But it's origin symmetry. That's right. Here is an odd function. X cubed is an odd function. Sine is an odd function. Okay? So it's origin symmetry. It's opposites in, opposites out. Okay? So on your picture, you know, if you go right and then up, you would go left and then down. Right? Opposites in, opposites out. Now, a lot of functions aren't either one. Right? I mean, if you took x squared, which is an even function. Now think about this a minute. If you took x squared, which is an even function, and shifted it to the right 2 units, is it an even function? Not anymore. It doesn't have y-axis symmetry anymore when you move it right or left. And take x cubed, if you moved it up or down, right? Or left or right, you wouldn't have origin symmetry anymore. So most functions aren't either one. So like on the quiz, I might ask you, you know, is this function even, odd, or neither? Right? It might be neither. And then you tell why it is. Now that's where you might get to use your calculator. I may give you an equation, and you'll put it in your calculator and look at it and say, okay, is this even, odd? Yes, Keith.
Does cosine function be oddly?
Very good. Yeah. If cosine was shifted, it turns into sine. So the basic cosine function is an even function. But as soon as you shift it and move it, it might not be either, or it could turn into even, right? Or it could turn into odd, because it could turn into a sine function, absolutely. And then here's the fancier way of writing this. F of negative x is equal to the opposite of f of x. In other words, you put opposites in, x and negative x, you get opposites out, f and negative x. Okay, opposites in, you get opposites out. So for example, on the sine curve, well, let's do the cube. If you take negative x and put it into cube, that's the same as negative x cubed, like that. Because you have negative times negative times negative. You have 3 negatives. So that output would be negative. Okay? Whereas with sine of negative x is the same as negative sine of x. Now let's think about that in terms of flips. A negative on the inside should be what? A horizontal flip, right? If it's on the inside, it works horizontally. So sine negative x should be a horizontal flip, which would be what? This right here. And this is telling us that that's the same as a negative on the outside, which is a vertical flip. But isn't that blue also a vertical flip? It's both. It's a horizontal flip and a vertical flip. Look at an even function. A negative on the inside would mean a horizontal flip. What happens if you do a horizontal flip on this? You get the same thing back. So it makes sense that a horizontal flip is the same as no flip at all. Okay? So it kind of fits in with what we're talking about. Okay, last thing. Periodic. A periodic function. Now, as soon as you heard me say periodic, what came to mind? Chemistry. Oh, well, that's good. This is Lars be happy to hear that.
Tell her next one.
Yeah, that's good. Periodic function, what comes to mind? Sine, cosine. Okay, if you had to describe to somebody who didn't know anything about periodic functions, you had to tell them what it looked like, what would you say? Wavelengths, same thing over and over again. Repeats, right? The word repeats would probably be in here. Now, we got to be a little more technical than that. If I gave you a function that did this, would you say that's periodic? Does it repeat? I mean, in one sense of the word, you could probably say that repeats, right? But that's more of a pattern. It has to repeat what?
the same outputs have to repeat. So this would not be a periodic function. It has to repeat horizontally. It has to repeat the same output. So let's put that down. It has to repeat the same outputs, at regular intervals. And the regular interval is the period. That's what we call the period. Like sine has a period of 2 pi, because every 2 pi it repeats the same output. Okay? If you take the sine graph, right, every 2 pi units it repeats that output right there. Now it does have that output some other times, but every 2 pi units it will repeat that output. Now here's the fancier way of writing it. Okay? F of x plus p is the same as f of x. In other words, if we horizontally shifted one period, if you took sine and shifted it either way 2 pi, it could land right on top of itself, right? That's what that's saying. Actually, you can do any multiples of that, right? Move it 4 pi, 6 pi, it would just land right on top of itself. Now, I might ask you some questions, though, in a little different way, and there's some on your homework, and there'll probably be some on the quiz. If I tell you f is periodic, and I tell you f of 2 is 7, and it has a period of 5, and I ask you, what's f of 17? Could you tell me? That's all I tell you about f. Is f of 2 is 7, and it's periodic function with period 5. Could you tell me f of 17? It's 2. Why? Because every 5 units it has to repeat the same output. So at an input of 2, you get 7. What's the next input you're going to get 7? 7. Next one, 12, 17, 22, right? Every 5 units you go over, you're going to get out 2 again. We don't know what's going on in between, right? So you're looking at this number, you're looking at this number. Another way to do it is say they're 15 apart. That's 3 periods, right? So f of 2 and f of 17 are 3 periods apart. They have to have the same output. Yes?
Why would you do 1 to 7?
Oh. Is there a rewind button on here somewhere? Yes. Thank you. I was thinking, I don't know what I was saying. Yeah, well, I think I was saying the right thing. I was saying it has to repeat the same output, but I put a 2. It should be 7, right? It's got to be the same output. Yes, it's got to repeat. So every 5, let me try it again. So every 5 units, so when you get 2, you get 7. At 7, you'll get 7. At 12, you'll get 7. And at 17, you'll get 7. Yes, you'll keep getting that over and over. Now, what about this? Let me ask it a little different way. True or false? True or false? The period's still 5. So it's true, right? We don't know what f of 4 is. We don't know what f of 9 is. But we know they got to be the same because they're 1 period apart. Okay, so just some notation. Those are notation kind of things, plus this idea of periodic function. So I think we know what a periodic function looks like if we see it. So if I may give you a graph, say, is it periodic? But I could also ask you some questions like this. So you got to understand notation and then understand the concept of period. Okay, so you got the rest of the time to work on the 1.2 homework questions. 1.2 homework questions for tomorrow. Remember that calculator scavenger hunt is going to be handed in tomorrow. Okay. Yes, sir.
I'll be done.
Oh, right.
And so,
Okay. You gone all day?
we're here first one.
Okay. You know, it'd be nice if you'd give me that scavenger hunt, come in and drop it off. It would be good. But we will be talking about 1.3, which, to be honest, when it comes to the quiz on Tuesday, as of today, we've already talked about the vast majority of what's going to be on there. And Monday's going to be mostly trig review stuff that's not even on the quiz. I mean, you know what I mean? So, so I'll have the video up. So, some exciting weekend, review it.